So in the previous subpart, we talked about the symmetry or how the Newton's second law of motion changes under different space-time transformation like the spatial translation, spatial rotation or the time translation. Here we will talk about some more transformations. To start with, we take time reversal. Time reversal means the study of the evolution of a dynamical system if we assume that the time is running backwards, right? So it will be always in the reverse direction of its natural evolution. Technically, this type of transformation can be perceived if we simply make this transformation t2 minus t. Let's say we are considering 1D motion of a particle and the particle starts from some point A over here, and after some time t it should reach B following this path drawn over here in magenta. But now if we assume that at an intermediate point P, okay, during its motion suddenly the time starts flowing backward, then the question is whether starting from P the particle should retreat its own path or recover its own path, following which it reached really at P from A or not. Okay, if it really recovers its own path and reaches back to back A, then of course we will say that the evolution is symmetric under time reversal. Okay, now we know that the governing equation is Newton's second law, so we just write Newton's second law over here. Okay, this is d2r dt2 is equal to F. Now under time reversal we know that r is not affected, the position vector is not affected. That means the P, when exactly at the instant when time starts flowing backward, the position vector remains at P. So it doesn't really changes because the particle is over here. So the position vector from some origin should not change, right? But the T is now changing to minus T. In fact, if we start after t0 seconds, it depends on how we make the initial instant in our watch. Okay, if we just make the initial instant at t0, that means if after t0 seconds of the real start from A, the time reversal is done, then basically t prime will be t0 minus t and not minus t only. But in both cases, you can see that dt prime will be equal to minus dt. That means the changes will have the different signs, right? Now, if t2 is transforming to minus t, then the velocity in the new evolution process will be simply minus of the old velocity, right? But as time is changing its sign twice, in the acceleration we cannot see any change of sign, right? That you can understand easily. So the left hand side, again we can say that after the time, under the time reversal, the mass is also unchanged. So the left hand side of the Newton's second law is unchanged. The question is whether F prime will be equal to F or not, right? So in usual cases, the gravitational force or electromagnetic force, from our experience, we can actually show that they are very much symmetric under time reversal symmetry, right? So these two forces are, of course, time reversal is symmetric, and that's why we, in the language of thermodynamics, as you all learned, I hope, that it is known as the evolution under such forces are known as reversible evolution, right? However, if we include macroscopic effects of dissipation, that is friction force or electromagnetic field with some absorption in a conductor, for example, then we can have dissipative effects. And as you know that whenever there is some dissipation, there will be irreversibility, and we can have violation of time reversal symmetry in the classical systems, of course. Okay. So my question to you is to study on internet or in books, what about the strong and weak nuclear forces? Can you tell me? Okay. Now note that time reversal actually switches the direction of velocity but not for acceleration. So that is something very important. and to always remember. Okay. Now we also can note that electric field is invariant under time reversal, but magnetic field changes its sign. Can you also feel that? Okay. And also, if you somehow feel that and if you are convinced with that, can you also say what about the Lorentz force, which is V cross B, and the Poynting vector, which is E cross B? Of course, this is then, I mean, once you are convinced with that, you can easily say about that. Because V is changing its sign, M is not, E is changing its sign, B is not. So, well. Now, coming to another type of transformation, which is known as mirror symmetry, which is a special case of parity. Parity, you can read in standard textbooks what parity is. So, mirror symmetry is uh, whether the laws of physics are identical to some system and its reflected mirror image or not. That is our question. Now in physics, several entities are having this mirror asymmetry. It is called the chirality problem, okay, or the handedness. I mean lack of handedness symmetry or something, right? So that is the coil, corkscrew, this type of thing, okay. So let's say for example here it is drawn like if you just think that I have translated here this coordinate system, which is the right hand corkscrew coordinate system rule. So right handed coordinate system, Cartesian coordinate system. But if instead of translating this I also like this vector, I would have taken this the image or the mirror reflection of this original coordinate axis. Actually you can see that that would be a left-handed Cartesian system. So this type of things are there, and sometimes some laws of physics are should be or rather are expected to be independent of this handedness. That means the motion of a projectile, a falling body, vertically falling body under gravity, all these things are in general independent of handedness, right? Now we have to do something general and to show that whether and how and when Newton's law of motion, second law, is invariant under such transformation. So let's assume a mirror in the xz plane, as you can easily understand, okay, and this vector A is reflected through this mirror to A prime. Okay. Now we are measuring these two vectors by the same Cartesian coordinate system, both are right-handed. Okay, and we will see simply that only the component which is perpendicular to the plane of mirror has changes its sign, and the components which are lying on the plane of the mirror, they are not changing their sign. Now if we take this arbitrary vector to be the position vector, we can easily say that x prime is transforming to x and z prime is transforming to z, but y prime has changes its sign. Same thing will be perceived for the velocity and acceleration vector. Now there is nothing for time and mass, so they will be unchanged. Now the question is, for N to L to respect this mirror reflection symmetry, what will be the necessary condition? The condition is simply that the fx, fy and fz should exactly follow the transformation rule of the position vector. And all the vectors in physics who are obeying these transformation rules, they are called true or polar vectors. So the conclusion is N to L respects mirror reflection only if the force is a true vector, and in general it is like that for ordinary cases. Now if we make the cross product of two true vectors just by expanding the individual vectors and using this transformation rule for the true or polar vectors, you can easily see that for the cross product of those two vectors we can see this transformation rule and not the old transformation rule, right? And this transformation rule is called the transformation for an axial or a pseudo vector. Okay. Now, like the vectors, we also have real and pseudo type of classification for scalars. A real scalar does not change its sign under mirror reflection, whereas a pseudo scalar should change. So it is the opposite of the vectors. Okay. One thing is very interesting. In weak nuclear reaction, time reversals, it should be mirror reflection symmetry. Okay, it is mirror reflection symmetry. Yeah, let me just like this. Mirror reflection symmetry breaks down since the potential function of weak nuclear force contains a non-zero pseudo-scalar part. That's very interesting. We will try to understand. So if it has a pseudo-scalar part, then in the force you have a pseudo-vector part, and that basically makes the system a bit complicated. And the force is not the corresponding force to be not really a pure polar or true vector. Okay. My question to you is, how do the vectors or pseudo vectors change under parity? Parity is the general transformation I told you to study, where in usual sense we say that any of the three components changes its sign, but in quantum mechanics or in theoretical physics, parity just simply says that it is the reflection about one single point. That means all the three components will change its sign. Okay, so just think about it. Then coming to this transformation, which is simply very interesting, that is the Galilean transformation, and that relates all the inertial frame of reference. We all know by Newton's first law that they should be equal. So what are inertial reference frames? All the reference frames which are free of any net external force, and they are moving with respect to each other with a relative speed which is constant u, relative uniform speed u. And we have to study whether in such reference frames the laws of physics are same or not. Now under this transformation, if you just think of two reference frames and their origins are coinciding at the initial instant, but after that one is moving, for example the prime coordinates are moving in this direction with a velocity u, okay, then their coordinates would be simply related by this equation. So x prime will be equal to x minus u xt, y prime will be y minus u yt, z prime will be z minus u zt, and t prime will simply be t, because the motion would not change time in non-relativistic case, right? All the ux, uy and uz, they are constant because the speed is uniform. Okay. Now Galilean transformation, as you can easily recognize, this is nothing but another transformation of the space coordinates. But now this is not by a constant amount, but this is an amount which is linearly proportional to time. Hence the velocities of the particle will be related by this. V prime will be v minus u. But the good news is, although velocity changes by a constant amount, the acceleration doesn't. And the mass also is not changing. So again, the left hand side of the Newton's second law is unchanged before and after the transformation. So in order that n to L be invariant under Galilean transformation, f prime also should be equal to f. And what is about f? Again, we know that f's are, in usual cases, f's are depending on the relative distance between the source particle and the test particle. And here this is both of, as they're, they're depending on the relative distance, and this is nothing but again another case of space translation. So finally the relative distances are not changing, so f prime is simply equal to f. You can easily see. So n to L should be, for usual cases, natural forces valid under, symmetric under Galilean transformation. Note that, however, Maxwell's equations are not invariant under Galilean transformation. A more general transformation, which is called Lorentz transformation, is required to prove their invariance, and that is the relativistic case. Now, Lorentz transformation reduces to Galilean transformation for velocities which are very, very less than c. For the interested students, if you are interested, you can have a look to a subset of Maxwell's equation, which is called the Bianchi's subset. And that subset is somehow invariant under Galilean transformation. You check and tell me which two. So there are two of the four equations there making a subset who are satisfying Galilean symmetry under Galilean transformation. Okay. Finally, this was the story for inertial frames. Finally, how to relate non-inertial frames in Newtonian framework. As we all know, N1L first law says that all the inertial frames are equivalent. And previously we also showed that N2L is symmetric under Galilean transformation. Now we have to study how the law of Newton is modified if one of the two frames is non-inertial. For simplicity, at the first step, we assume that one is moving with respect to the other with a uniform acceleration a. A in general need not be uniform, but here we just assume that, and if we assume that, you can simply write this transformation rule. Okay, you all know, right? So x prime will be x minus half ax t square, where a, y, a, z all are, and I mean all are uniform because a is a constant vector. All are constants, so a is a constant vector. T prime and m prime, they are simply equal to t and m respectively, simply because t and m, they are not affected by the motion, mechanical motion of the system, right? And finally, and also mechanical motion of the frames of reference. This is also, like whenever I say that t is not affected by this change of the space coordinate translations, this is also giving you the essence of absolute space and absolute time concept in Newtonian framework. Okay. And again, we can say f prime is equal to f. Have you understood why? This is again the case of another type of space translation, and the relative distances are necessary. And you can see that, you will see that this is simply the case of this previous cases of space translations. Okay. And finally, if you just do this translation, you can work out about this, the transformation of the velocity, where you can see that the velocity is now translated by an amount which is linearly proportional to time, but acceleration or the force is translated by a constant amount which is ma. So f prime minus ma is equal to m dv prime dt prime. So if this one is our new f prime, let's say f prime representative, the total thing, then we can simply say that Newton's second law is valid even for this non-inertial frame of reference. And this extra term which is required for this equivalence is known as pseudo force. Okay. In the tutorial, we will talk about more general cases, which is the case of rotating frames of reference. Thank you very much.